Hi everybody. I thought I will go through this worksheet that you have on standing waves in strings and pipes. And this lesson is actually in your booklets, and it is this page which says standing waves in strings and pipes. So what we have here are four strings that are fixed at both ends, and this one are similar four strings which is just fixed at this end. What I usually do in the classroom is I give people a piece of string. I don't know if you can see that, and if you twirl it between your fingers, you can actually see standing waves being formed. And I don't know if it's visible here on the thing, but I hope you can see that. Okay, so have a play with a piece of string, just twirling it between your fingers like this, and it's quite fascinating. You can see all these different standing waves set up on the string. So in this particular example, we've got to draw the fundamental. So now when you have a string or pipe that's resonating, only certain frequencies that fit the length and the restrictions of the string or pipe are formed. And the most important standing wave that's set up on a string or pipe is what's called the fundamental, and this is the one with the longest wavelength. This is the simplest one, the one with the longest wavelength. Okay, and so longest wavelength will mean smallest frequency. And the fundamental is also called the first harmonics, and the other harmonics, they're also called overtones. The higher harmonics are all exact multiples of the fundamental, and I'll explain what we mean by this. And so what we have to do is, in these diagrams, we've got to do the fundamental or the first harmonic and the first, second and third overtones in each of these, given these restrictions. So these are strings fixed at both ends, string that's only one end fixed, one end closed. This one is a set of four pipes that's closed at one end, open at the other, so they're referred to as closed pipes, and these are what we called open pipes. So, and then what we have to do is we have to calculate the wavelength, given that the length of the string is 1.5 meters. So I'll just write the length is 1.5 meters. So how do you draw the fundamental? So the fundamental is the simplest one. Because the ends are fixed, you have to have a node there. So this is the shape of the fundamental. So you've got the node at both the ends and the antinode there. Okay. The next one, you always have to have the node there, but the next higher harmonic will look like this. Okay. Two nodes with antinodes. So it's one bubble, two bubbles. And this one, the next one will look like that. And then the one after that. Okay. So how do you calculate the wavelength of this wave? So this is only half a wavelength because only like one crest or one trough. Okay, so and this whole length is 1.5 meters. So half wavelength is 1.5 meters. So the whole wavelength is 2 times 1.5, which is 3 meters. So that's how you do for this one. Okay. For the next one, your whole wavelength is 1.5 meters, so which is the same as the length because that's a whole wavelength. Now this one is 1.5 wavelengths, the third one. So 1.5 wavelengths, 1.5 is the same as 3/2. So 3/2 wavelengths is 1.5 meters. So your wavelength is equal to 2 times 1.5 divided by 3. Okay, and so that's 3 divided by 3, you get 1 meter. So that's how you calculate the wavelength, and this one's actually 2 wavelengths, the whole length. So one wavelength will be half of that, which is 0.75 meters. So that's how you calculate wavelength. I'll just rub this out, otherwise it's going to get too crowded. Okay, the next one. So the simplest wave that can be formed in something that's fixed at one end, open at the other, you have to have an antinode here and you have to have a node there. So an antinode looks like that, node looks like that. So that's your simplest one, that's your fundamental. Okay, and what's the wavelength of the fundamental? So this is only kind of half of this, which is only quarter a wavelength. Okay, so quarter a wavelength is 1.5 meters. So a whole wavelength is 4 times 1.5, which is 6 meters. So that's the wavelength of this. Okay, so the next one, you always have to have an antinode there, a node there. Between nodes and antinodes, you've got to have, and you can have another node. So I'll just rub those off to draw the shape, keeping those in mind. Now, when you draw these diagrams, you really have to be careful because that's only quarter wavelength, that's half. So that length should ideally be twice this length, okay? Just have to be careful. And then the next higher harmonic. And the next one looks like this, okay? And just looking at the wavelength for this one. So how many quarters do we have? 1 quarter, 2 quarters, 3 quarters. Can you see that's half and a quarter, which is 3 quarters? So 3/4 wavelength is 1.5 meters. So a wavelength is 4 times 1.5 over 3, and you get your answer. Okay, the next one too, we'll see how many quarters there are. So if you do it in multiples of quarters, then it makes it easy. So that's 1, 2, 3, 4, 5 quarters. So you get 5/4 wavelengths is 1.5. So your wavelength is 4 times 1.5 over 3. And you get your answer, which is 6 over 3. That's 2 meters. Okay, and so on. And this one will be 7 quarters because it's 1, 2, 3. That is 6 quarters plus another quarter. And that's 7 quarters. So, and you can work that out. Okay, so I'll just write this out. This one here, for a pipe that is closed at one end, open at the other, you always have to have a node here. So it's very similar to that, but it just tilted the other way. So this is the first one. And then your second one will look like that. And then your third one and then so this one and that one's identical, only thing it's the other way around. And you calculate the wavelength the exact same way. So remember, nodes are there at the ends. You've got your antinodes at the top and additional nodes and antinodes depending on the shape. Okay, and then the last one's actually exactly like this, but just a little different. If the pipe is open at both ends, you have to have an antinode at both ends. So always between an antinode, you always have a node. So this is the shape of the wave in an open pipe. There you go. Okay, and then so what is this wavelength? So this is actually a quarter, that's another quarter. So this is actually half a wavelength. So half wavelength, and I think the length of the pipe is 6.25 meters. So wavelength is 2 times 6.25, which is 12.5 meters. And this one is a half, and then there's another half here, quarter and quarter. So that's a whole wavelength. So your whole wavelength is 6.25 meters, which is the same as the length. So this is 1 half, 2 halves, so that's a whole, and this is a quarter and quarter. So that is 1.5 wavelengths over here. And so that's how you work these out. So I hope that made sense. Bye for now.